Decoding Dirac. Well, fundamental physics is all about fermions and their interactions, which includes the bosons. There's nothing else, that's all there is. And we've had explanations for these things for a long time. We've had quantum mechanics, relativistic for a fermion, for nearly 100 years now. It's hard to think it's so long ago. We've also had the standard model for classifying fermions and everything for nearly 50 years. But we still don't have a fundamental explanation of everything. We've got the ingredients, but we haven't got the fact. And why is that? Well, the first answer I would give, that's the barrier to this, is that the mathematics is being used without meaning. We've got quantum mechanics, quantum field theory. We often see those in a black box way. And we've got mysterious things that we don't really explain, like wave functions, creation and annihilation operators and stuff like that. And the Dirac equation has the gamma matrices, which are just introduced just to make it work. They're the only things that make it work. I don't think we should see mathematics in physics equations in that way. I think we have to see mathematics as coding physics. And we should look for what it means as well as how it works. So we need to decode as well as apply mathematics, which means going beyond deductive techniques. So this is the Dirac equation, well known to many of you. And the gamma terms, 4x4 matrices, mutually anticommutative, some square to the identity matrix, others to the minus identity. They're all mutually orthogonal the three, 1, 2, 3 are mutually orthogonal components of a vector type thing. Now there's yet another matrix which will help to close the algebra, which is another square root of I and anticommutative to the rest. But that doesn't appear in the equation. And this is one set of gamma matrices, and there are many such sets. But this is one that's commonly used. These can be derived from 2x2 Pauli matrices. So if we put 2x2 matrices in there, we can extend them to 4x4. And that's what the Pauli matrices look like, as everyone knows. This is quite an extraordinary structure. How is it that a fundamental equation in physics suddenly has to have this matrix structure? It suggests that there must be some powerful physical meaning behind it. And when we look at mathematics used in physics, we've got the standard model, and there's a lot of meaning absent from the standard model. It's got a lot of symmetries, groups, formalisms, but we don't really know where they come from. The first thing is that the gamma matrices form a group. There are only 5 gamma matrices, 5 base ones, though there are many versions of them. But there are 64 identifiable products when we include plus and minus. So this is a group of order 64. It's a closed group of order 64 requiring just 5 generators. But the important thing to realize is that the equation doesn't need these matrices. It just needs an algebra with the same properties, that the gamma naught and gamma 5 square to an identity, or even 1, and the other 3 square to -1, and that they're all anti-commutative with each other. And there are a lot of other algebras which are defined by these operations. As far as I know, they're all Clifford algebras. And a lot of authors have looked at Clifford algebra as an alternative to the standard gamma algebra. And as far as I can see, a lot of mathematical simplification has happened, but I don't see a lot of physical insight. So if we look at Clifford algebra, we've got to look at which Clifford algebra and why. I think there's one that has a special meaning physically. And this is one that I had before I even applied it to the Dirac equation. I was using it for other things. And it's a combined algebra of the 4 fundamental physical parameters: mass, time, charge, and space. These form a Klein 4 group and also include the notion of zero totality in the universe. And that's a version of it. This diagram, I got my friend Vanessa Hill to draw this nice diagram for me, and this is the nice diagram. And As far as I know, this is a perfect symmetry in the global sense. We'll show what we mean by going from the global later. So the properties of the parameters considered separately are global. But when we create locality by combining them into a minimal structure, we create locality and things change. And remarkably, these properties can each be simplified into an algebraic structure. So mass, by which I mean mass energy in principle, because this is a global thing, not a localized thing, that's got scalar properties, and the unit is 1. Time is the complex numbers, unit I. Charge, this is the most innovative thing probably, is that this is a quaternion with quaternion, a kind of dimensional square roots of -1. And space is a vector, and by which I mean, by vector entirely in this presentation, I mean what Heston has called multivariate vectors, which are isomorphic to Pauli matrices, which are complexified quaternions. They have more properties than ordinary vectors, but they are real vectors do have these properties. Now, if we put those 8 units together and take a tensor product, multiply them all out, we also get a group of order 64, which is exactly isomorphic to the gamma algebra. And what's particularly interesting about this is that if we take apart the 4 complex numbers and look at the remaining 60 terms, they arrange themselves, or can be arranged, into 12 pentads. So if you look at the first line underneath the complex terms, I, etc., there is 5 positive terms on the left and 5 negative terms on the right, and each of those 5 is what I call a pentad, and the ones below are arranged in pentads in the same way. Now, if you take Clifford algebra, complexified quaternions become vectors, complexified vectors become quaternions. And so we can, in principle, combine the the ordinary complex I and the ijk quaternion into a new space-like structure with the same properties as a space. And I'm going to write that one in red, ijk. And we can write the group, that's the quaternion vector 1, this is double vector 1, as a double vector algebra. In fact, I don't think I changed 1 or 2 of the quaternions into vectors, but just treat them all as vectors, double vector algebra. And this division into 12 pentads is extremely significant because each of the pentads incorporates every one of the 8 basic algebra units that we started with. And each is a generator of the 64-part algebra, sometimes when complexified, but that will not be a problem. 5 is the minimum number of generators for this group. If we attach to the units of any pentad the scalar factors, let's just call them px, py, pz. These are just numbers, scalar numbers, em. Then we will get an object which squares to e squared minus px squared minus py squared minus pz squared minus m squared. And if those things should happen to be connected with the energy, momentum, and mass, then that squaring would be 0. So the object which we squared would be a square root of 0, or a nilpotent. It's very significant that the algebra of the Dirac equation is the algebra of a double space, and it's also a dual space, which means that information in one space can be transferred to the other, and we will show an example or 2 of that later. And it's also a double Pauli matrix algebra. Now, we don't normally realize this because we don't normally use the full 64-part algebra when we're using matrices. So this double Pauli thing isn't normally recognized. However, the Pauli, this is showing how our vectors are a bit more than ordinary vectors. They have a full product, A dot B plus I A cross B. And Heston has applied this to the momentum, or the gamma dot del term in the Dirac equation, and show that this incorporated spin. It was automatically incorporates spin. Now, we only need a pentad to generate the entire algebra, so we don't need all the 64 terms normally. So what we really need is dual spaces, and that's all we need for relativistic quantum physics. There isn't any other physical information available. And if I write one space in blue, this is the space that we normally think of as space, the space of observation and measurement. And the other, which I'll write in red, contains everything else: charge, mass, time, anything else. And I call that vacuum space. And it's the intersection of these two spaces that creates the singularity that we call the fermion. The fermion exists on the boundary of two spaces, only one of which we can see. We will keep this red and blue coloring throughout this presentation, and so you can follow where each space goes to. Now, if it's a dual space structure, we have an immediate insight into such things as a point particle, because it's the intersection; spin a half, because it's half in one, half in the other; Berry phase, similar to spin half; Zitterbewegung again. What vacuum is, a space that we can't see; CPT, and so on. And also, Garnet, your complementary paths could be adapted to this framework. And the fact that it's generated from 5 asymmetric generators, because we will look again and we'll see they're asymmetric, gives us some inkling of what symmetry breaking means in the standard model. And what I'll also say is it produces a much more compact, powerful formalism for relativistic quantum mechanics, quantum field theory. And a lot of the existing apparatus will be shown to be redundant. In fact, more than 98%, and in fact, more than that. So let's have a look at this compactification when we're bundling all these 64 units into just 5 generators. This, in my view, becomes the origin of much of the symmetry breaking in physics. The lowest state, which is 5 generators like that, is not the most symmetrical. If we look at that, we can see that the three red generators there don't attach themselves to the same sort of object. So, and we'll look at that later. It's not the most symmetrical, which would be the double space, which is 6 generators. So nature always chooses the simplest or the lowest state. The lowest state isn't the most symmetrical. Now, if I go back to my quaternion vector representation, which is the one I will be mostly using, if I write out the 8 units on the top there, I now take the 3 charge units, the 3 quaternion units, and attach them to the rest. And we can see why those charges do not any longer behave the same when they're in this compactified, localized state. The K attaches itself to a pseudo vector, that I, that extra complex I. It's a pseudo vector. The I attaches itself to the 3 vector states, and the J attaches itself to the unit 1. So our blue space, our ordinary space, retains its symmetry, its rotation, symmetry, and the rest. The other one, associated with charge or vacuum, breaks it. And I would say now that the charge IK, the K is the one with the weak characteristics. The one attached to the vector is the one with the strong characteristics, and the one attached to the unit has the electric characteristics. We can now set about matching the 5 gamma matrices to one of the pentads. For example, we could do the first one, or we could do the second one in those. Sorry, the first one is vector quaternion, the second one is double vector, but we could do either. And there are lots and lots of ways we can do this, but the overall structure is the same. But in every case that we do it, we'll find out one symmetry of one three-dimensional quantity is preserved while the other is broken. Now, people have argued, and sometimes with me, that we've got a Dirac formalism that works. We've got the equation, we can use it, so why change it? Well, it certainly works in the equation, we can do calculations, but my answer is that it doesn't work for what we want it to do. It doesn't give us the standard model. And even people who've introduced Clifford algebra have quite often only done it once to the momentum terms instead of doing it twice to the whole equation. And we got a whole apparatus of mathematical objects which have been created, which I don't think are necessary. Spinors, primitive, idempotent, minimum left ideals, that sort of thing. Huge load of mathematical apparatus. I think nature is a mathematician, but an accidental one, not a clever one. So the existing formalism doesn't have the symmetry that I think it should have, and there's a lot of redundancy and fragmentation. Now, if I may be allowed to quote David Deutsch on a popular book of his, he talked about how certain things, after a period of limited parochial application, at some stage develop universality, by which he means a massive increase of power leading to unlimited application. And quite often leading to developments which were never imagined by the creator. And good examples of that are numbers themselves, mathematics itself, classical physics, the digital computer, but there are many others. We now have the opportunity, if we want to look at it this way, to develop this universality in quantum mechanics, if we can find a principle that has unlimited and universal extent. So back to the Dirac equation. This time, we've actually multiplied the matrices by the operators, the d by dt and d by dx and so on, and put them all in one 4x4 matrix, multiplied by the wave function on the right, which is necessarily has 4 terms, but we won't bother about that for a minute. This is what we get if we try to find, just for the free particle, let alone a complicated solution, the free particle amplitudes, and these are not the wave functions, they don't have any phase factors on them. Those phase factors are all different, and we've got these amplitudes are what we get. The solutions have different phases, as I've mentioned. First 2 positive energy, second 2 negative energy. And we've got E and M, if we look back, we got E and M mixed up. We got PX plus IPY. Well, I don't think that is something that is natural. Momentum doesn't split in different directions in that way. No counterpart in nature. And if we do that, if we put an IP instead of a P, then in principle, we're distorting the space-time signature to 2 pluses and 2 minus. So the problem, if we use matrices, we can get calculations done, but we get a fragmented equation. We get a fragmented solution which isn't complete for a real particle, for a free particle. And we mix up energy, momentum, and mass horribly. And also, it's a huge amount of logical space taken. 16 units in the matrix and 4 units in the wave function. That's 64 pieces of information just for one operation. They also lack symmetry. There are 5 terms in the equation, but only 4 have a gamma matrix. And yet there is a 5th term in the algebra. So what we need to do is defragment it, separate out energy, momentum, and mass from each other. So as you've probably done if you've defragmented your disk, which is where I got this idea of a diagram from, you get that jumble when you start, and when you finish, you get something like that. And so if we can separate out separate bins for energy, momentum, and mass, then we've defragmented it. At the moment, we don't have that in that matrix. So let's choose some algebraic operators. By the way, it doesn't matter whether they're plus or minus signs. It's irrelevant for this purpose because we'll end up squaring anyway. So we've got, that's one set of terms on the left and one set of terms on the right, A and B. Those are just taken directly from the diagrams. If we choose mapping A, that's what we would get. And now we're going to do something that seems to be trivial, but in fact it has profound consequences. We multiply from the left by j. And that's what we get. We get that equation. And now we can see we have separated out our operators into a bin for energy, a bin for momentum, and a bin for mass, separated out by those red quaternion factors. Now, we'll find the real significance of this extra symmetry if we put a plane wave solution for psi. So the plane wave solution there, a to the e exponential to the minus IE t minus p dot r. Then we put that in, and what happens after we differentiate it is that we get the same term multiplied from the left by that bracket beginning with ke. And if I gather the three momentum terms together, I get the last equation on the page. Now, the important thing there is that if we recall what we were talking about before when we put E, P, and M to those operators, if we do that bracket times A and times the exponential term, we get 0. The exponential term doesn't help us to get 0. That can never be 0. So it's the bracket times A, that's 0. And there's only one way of doing that. It's only valid if A is actually the same as the bracket. That, or multiplied by a scalar, which can be normalized out anyway. So A is a nilpotent or square root of 0. That's what A is. It's also completely explicit. We've actually got a solution which is completely explicit. There's no black box wave function or anything like that. And we multiply the equation from the left, multiply the operator, but that didn't in principle affect the wave function. So the wave function must have always been a nilpotent or have the potential of being one. Now we know that the conventional Dirac equation tells us there are 4 solutions because we've got a 4-component spinner. With this new symmetrical form, and with the knowledge from Hestiners that the multivariate P already incorporate fermionic spin, we can easily identify the 4 solutions: fermi and antifermi plus and minus E, spin up, spin down, plus and minus P. And we will need to apply those to amplitude and phase. And I mentioned another thing, connection with your work, Garnet, your space-time areas and your 4 colored lines. So we can represent the Dirac force spinner by column vector with 4 components. And so you see we've got 4 amplitude terms, if you like, and 4 phase factors, and each operated by a single operator. Now, if go back to that a minute, 4 phases, well, that is a calculator's nightmare. Even 2 phases is a calculator's nightmare. The only simple way of solving equations is to have a single phase. But we got the opportunity to do that because we've got rid of the 4x4 matrices. The differential operator is just a single term. So we got a logical space to add an extra twist to the symmetry by making the operator a 4-component spinner, identical in its representation to the amplitude. So we get that. So 4 different operators, 4 different phase factors. What we've done is exchange one phase factor. We've exchanged the variation in E and P in the phase factor for the same variation in the operator. So instead of 1 operator, 4 amplitudes and 4 phase factors, we got 4 operators, 4 amplitudes and 1 phase factor. So these 4 solutions now show that they're just sign variations of 1. There's only 1 solution. It's just plus and minus. There's nothing else. There isn't 4 different solutions. There's only 1 with 4 sign variations. They're just drones of the first one. And with only 1 operator and 1 amplitude, in effect, we've reduced our information to 1/64th. That is by to less than 2%. So we got rid of 98% of the structure that we didn't need. And we've got the first explicit complete solution for a single fermion, for free fermion. There's no mysterious black box. Everything is a function of E and P. And this is also true, we will find, when the fermion isn't free. We never need to use the concept of wave function except just for convenience of representation. We don't actually really need it, as we will see. And clearly the Feynman representation of negative energy states, negative time, automatic, because we've matched up the operator with the amplitudes. And so we can use the expression. I'm now going to slightly change my symbolism because I'm going to change the first expression there into the second, so I can put the imaginary part in a more convenient place for future reference. By the way, it doesn't matter what plus and minuses are, we can always switch those around. Whatever happens, that bracket remains a nilpotent, and the expression that squared equals 0, and it's convenient to represent the first by a row vector and the second by a column vector, becomes a perfect expression of the Pauli exclusion principle, because you cannot have two wave functions the same. Now, here we've got a scalar product. We don't have any matrix product at all. We just have a scalar product. And now if we go back to the Dirac equation, we could derive it easily from the Einstein equation, E squared minus B squared minus M squared equals 0. We simply factorize it. And then we apply canonical quantization to the first bracket, and we get the free particle Dirac equation in that form. No size in this. We can also use the convention that E and P represent operators as well as amplitudes to write it in the form below. So the first bracket is an operator, the second bracket is an amplitude. But the amplitude is always nilpotent. And we can also quite clearly create the Klein-Gordon equation by doing both brackets at once and changing those to operators. Now, the important thing about Pauli exclusion is that we never measure it for free fermions because we can't. We realize it exists for fermions which are in a non-free state. And so this is an important step now, and this is where we might get somewhere towards universality. This is a revolutionary step in many ways. We assume that all fermionic amplitudes in all states are nilpotent, and that the most general form for a wave function is nilpotent, and we should always seek a nilpotent solution for any problem. This means that we don't need an equation at all, not even the wonderful Dirac equation. We don't need any equation, we just need a Dirac operator. Relativistic quantum mechanics is completely specified by an operator looking like that. And that completely determines the phase that will provide a nilpotent amplitude. And when we find the solution, we're finding the phase. And as I mentioned, we don't need a wave function at all. We only need an operator. And as I mentioned before, this is very like, it reminds me of Cockney rhyming slang. If you say apples, then that couples with pears, which gives you stairs. Frog, toad gives you road. Dog, bone gives you phone. So you've got operator gives you a phase, which gives you an amplitude, and that squares to 0. So using the convention that we can always call it E or always call it P, simply because it's in that slot, that bin, then these can be covariant derivatives. We can have any number of field or curvature terms after the differential operators. And the expression below will always apply. Obviously, if it's not a free particle, the phase term won't be a simple exponential. But we can always assume that the amplitude is a nilpotent. So all we need to do is define an operator. This uniquely determines the phase factor, which makes the amplitude nilpotent. You don't need any equation at all. And that's what I'm saying below. Operator acting on phase factor squared equals amplitude squared equals 0. So we can now specify the 4 amplitude states as derived from 4 creation operators. These are the ones that make up the spinner, the fermion spin up, and so on. I'm not going to say anything about elasticity in this talk, although I could talk about it some other time. So the kind of particle we have is determined by the creation operator on the top of the column. That's just a convention. But the one that we've done is fermion spin up. If we wanted anti-fermion spin up, we would put the last term on the top and then follow the sign variations through. So I quote T.S. Eliot here, "Do I dare disturb the universe?" We have to. We can't avoid it. Anything at all we do disturbs the whole universe. The phase factor is simply an expression of all the possible variations in space and time encoded in the creation operator. And this is completely defined once you've specified the operator. And we can see then that fermion is really just a set of space and time variations. The mass term is important, but it's passive. And we can always find the mass given the other 2 terms because it's nilpotent. No system can be defined now as isolated. Defining a fermion will always disturb the universe, whatever we do. The energy conservation will only work out over the whole universe. And this will necessarily generate laws of thermodynamics because we've got to do the whole universe always. Now, this is an important refinement here. We can actually reduce the information even more if to a 2-term operator. And the wave function in this case becomes an amplitude without a phase factor. This is by using discrete or anti-commutative differentiation. And I'm following the procedure of Luke Kaufman here. We define a discrete differentiation of a function by preserving the Leibniz chain rule by defining the df by dt and d psi by dx and so on as commutators with E and with pi, the components of momentum. I'm going to take a case where we don't have velocity operators, so we can use partial df dt instead of full df dt. Now, the mass term, which I mentioned, is only passive anyway, disappears in the operator because it's a scalar and you can't have a commutator of a scalar. It just becomes 0. But it is retained in the amplitude. So let's define the amplitude. That's what a nilpotent amplitude would look like. And I'm calling it psi to maintain that convention. And I'm now defining my operator without a mass term. And if we do some manipulation, which I'm not going to do at the moment, but it's quite straightforward, we get the following: psi times the bracket plus bracket times psi minus 2i, and then that's obviously 0. And the whole thing is clearly 0 if the psi is a nilpotent, which means that we can write our operator times operating on psi is 0. If we generalize it to 4 states, we just put the plus and minus variations in, then we get the equation at the bottom. Now, this is important because we haven't actually used I or H bar in defining those differentials. We just define them without putting I, H bar. Now, if we want to use quantum versions of these things, we normally need to put I, H bar before them, but I didn't bother. And the reason why I didn't bother is because that equation at the bottom here, I can put I, H bar outside of the left-hand bracket, and it won't make any difference to the equation. But now it will be quantum instead of classical. And the force sign variations takes care of any plus or minus that we have on the I, because the del has a different as minus, while the d by dt is plus. But it doesn't matter, we've got the force sign variations. So we can make a smooth transition between classical and quantum conditions using this. Now, this is something that was brought up very early on when I was using nilpotent wave functions, that people generally believe to be the wave function for the Dirac equation is an idempotent and not a nilpotent. That means it's a square root of itself and not a square root of 0. And so it is if we choose to write it. Let's look at those two equations at the bottom. They're identical, except in the middle of the equations, you'll see that the red J is on one is in both J's are in one bracket, and in the other one they're in the other bracket. It's separate brackets. So we can write exactly the same wave function, exactly the same operator, and it's just a matter of where we distribute the extra J's. But the equation can be written either as idempotent or nilpotent. There's no change in the physics or mathematics. The wave function has both properties. And part of the reason for that is that I don't have a wave function. It simply comes out from the operator. And as I say, the wave function, the original conventional version, was nilpotent because we brought out its characteristics simply by multiplying from the left. The idempotent does have some value because it ensures the 4-component wave function acts as a spinner in the conventional version, and it's also useful for vacuum operators, as I'll show you. Now, I think the nilpotent form is optimized for calculating efficiency. And even if you compare it with the non-relativistic versions of quantum mechanics, it's much more efficient and much easier to use. We've got only one phase factor, so we can deal with everything in a single calculation. If you look at the normal way of the Dirac calculation of anything, it's always very complicated because there's more than one phase factor. But even more important is the extra constraint of nilpotency forces onto us an interpretation which connects every fermion holistically and non-locally with the rest of the universe. And we don't need a lot of the formal apparatus of relativistic quantum mechanics or even quantum field theory. I think it's the minimal version that we could do. So what I'm going to do now is do one example which everybody knows, or many people will know, which is the Coulomb interaction, the hydrogen atom, if you like. And this provides a model for many other cases, and which I've done. I've done cases that have never been done before by using this as a model and developing it. And if we want to consider the effect of one spherically symmetric point particle on another, we need a version of conversion to polar coordinates. In polar coordinates, it's difficult to maintain the Hester's convention about spin. So we really have to include a spin term, which is that J plus a half over R term. But I'm following Dirac's version with a minor exception which I'll mention on the next slide. So this is an adaptation of Dirac's version from his book on quantum mechanics. And I'm just writing the operator here. This isn't a hydrogen atom, it's just an operator for a free particle in polar coordinates. But if we want a nilpotent solution for this won't give us one. We can just inspect it and we will see that we will never get a nilpotent solution unless the KE term has some sort of term in 1 over R, like the middle term. So the first term, it has to have a 1 over R in it somewhere, because otherwise we won't be able to cancel out the 1 over R's and the 1 over R squared and so on. And of course, every interaction between fermions includes such a term. Even the strong and weak interactions have B0 field the weak and the 1 gluon exchange for the strong. So even they have a Coulomb term. So this is what if we put that Coulomb term in, and we're not even considering a hydrogen atom, just a Coulomb term for spherical symmetry is always there. But we'll do this now with the Coulomb term. Now, to establish its nilpotent, we have to find the phase which will create a nilpotent amplitude. And this will show you how we go about doing these sort of calculations. And I mentioned to John before that he said that at one point Dirac had effectively made something like quaternion I and pseudoscalar I into double quaternion I, or something equivalent. And looking at Dirac's solution, he does that with this equation, because his J plus a half term ends up outside the bracket entirely. So how do we get the solution? Well, we know the standard solution, so that makes it easy for us, because the biggest difficulty in getting a solution for anything like this is guessing what the phase term is. But this has already been done for us 100 years ago nearly. And below the equation, you can see the phase term. That's the standard phase term for this solution. Now, I'm going to apply that phase term, the differential operator to that phase term, and then I'm going to square it and equate it to 0 all in one go. And I will get that first expression on the top. And then all I've got to do now is easy. I just equate constant terms, equate terms in 1 over r squared and terms in 1 over r for the conditions that the conventional solution uses. So there's my constant, there's my 1 over r squared, there's my 1 over r. And if you're really good at doing algebra mentally, you will find that the solution for E over M is at the equation on the second equation on this page. It took me about 2 or 3 lines on paper, but it took me about 2 or 3 lines on paper, but it might be, some of you might be good enough to do it straight off. And if you are, then you could say you've got the solution for the hydrogen atom in just 6 lines. Now, this is a well-known solution, but could we do other ones? Well, yes, in fact, we can do at least 2 other ones for point particles, none of which have been achieved analytically. If we make if we add an extra term as well as the Coulomb potential, and this extra term is proportional to R, the solution has the characteristics of the strong interaction, infrared slavery asymptotic freedom. I'd like to be able to do that, but I haven't got time today. If we do any other polynomial collection of polynomials, inverse power series, so in any term in r to the n, or any number of terms in r to the n, or r to the minus n, as long as it isn't r, then we get a harmonic oscillator. Now that surprised me, but that is in fact what we get, which is a characteristic of the weak interaction, Fermi creation, annihilation. And that means that because we've exhausted the polynomial solutions, etc., and you can express most functions of polynomial, that virtually exhausts the possible nilpotent solutions. Now I say the nilpotent method gives us an immediate transformation to quantum field theory. We don't need all that cumbersome apparatus of quantum field integrals with creation operators that we don't understand and annihilation operators we don't understand. They're just symbols, but they don't say what creates them. But I say the creation operator is the differential object itself. And if we want to specify things completely, we have to do the interaction between the fermion and the rest of the universe, which is in fact what quantum field theory does, in effect, without saying so. The single factor makes calculation a lot easier than it would otherwise be. Now, the symmetry between E, P, and M is determined by having coefficients Ki and J. And this makes the significance of the second vector space apparent. I shall say something more about Pauli exclusion. We did it simply by nilpotency. If you multiply 2 wave functions that are identical, they will disappear. So it will automatically follows from nilpotency. So the combination state will always be 0. But if we do the conventional way of doing Pauli exclusion, that's, say we got antisymmetric wave functions. So we find psi1, psi2 minus psi2, psi1. So let me do it for 2 nilpotents. And what we get is a lot of expressions that disappear, leaving only an expression which turns out to be P1 cross P2 or minus P2 cross P1, which is in fact clearly antisymmetric. But it also tells us something incredible. It tells us that the only difference between two fermions in Pauli exclusion is the instantaneous direction of their spin vector. Just the direction. The magnitude is irrelevant. It's got to be the direction. That's the only reason why that vector product term doesn't disappear. So every nilpotent wave function has to have a p vector in spin space at different orientation to any other. And what I like to think of, the vector is perpendicular to a plane, and if all the vectors have a perpendicular plane, then all the planes must intersect corresponding to the different p vector directions. I also like to think that this helps to create the meaning of a Euclidean space. This is one aspect of it that I wanted to point out, that Pauli exclusion in real space is determined by this. In vacuum space, it's determined by the nilpotency. The nilpotency determines it in vacuum space, because that arrow, that thing coming out from the origin, has to be a unique direction for every fermion. And in real space, it's got to be a unique direction in the momentum component. And the diagram on the right tells us why a fermion can't be massless. Because if fermions are massless, then they would all be at the same angle. They'd all have this direction at the same angle. The formalism also forces us to realize that the universe can't be separated from the way to define a fermion. And now we begin to see what is vacuum. I've talked about vacuum space, but what is vacuum? Well, suppose we want to create a fermion from absolutely nothing, which is what I believe the universe to be, and that we put all its interaction potentials into it. We don't bother saying where they come from, but they act on that fermion. So we put everything into that E and P operators. Then that gives us the operator for that fermion, from which we derive a wave function, etc. So let's call it psi f. Now we pluck that out of nothing. What we're left with in nothing is a hole in nothing, which could be described as minus if if you like. So the hole in nothing is what's left when we create a fermion. And we can see that psi f plus minus psi f equals 0 as to the product state if the wave function is nilpotent. So the nilpotent structure and Pauli exclusion now become comprehensible. The entire universe adds up to nothing. The vacuum becomes the hole in nothing, which is left. But of course, the vacuum isn't nothing. If we want to create a fermionic state in that condition with those interaction potentials, then we can only do that if we create the environment in which those potentials can exist. That is the rest of the universe that's needed for that fermion to have those potentials, whose total effect adds up to minus f, psi f. So vacuum for any fermion state is the rest of the universe for that state. And that's what the fermionic operator is acting on. When it operates on something, what the operator? It's operating on the rest of the universe to create its phase factor. And the rest of the universe has to be constructed to appear to be the mirror image of the fermion state. And each fermion must have that condition. So we can say that Another version of Pauli exclusion is the statement that no two fermions share the same vacuum or the same phase factor. And nilpotency gives us a great definition of the difference between local and non-local. There's our nilpotent operator in that bracket. Well, everything inside the bracket is local. It obeys all Einstein's equations, etc. But everything outside is non-local. So if you superpose two brackets, or combine two brackets or more, then that's non-local. But it doesn't mean that they're separate. No, they're not separate. Local and non-local are just two sides of a coin. Local causes changes to non-local. A good example being if you do Young slits for electrons and you block up one of the slits, then you're making a local change which changes the non-local interference pattern. But also, local is caused by non-local. So Pauli exclusion is non-local, but it causes us to need a Coulomb term in the fermion. So these things always happen in tandem, and all the forces can be understood either non-locally first, and then you decide what the local meaning of that non-locality is, and so forth. So locality is about defining the fermion state, and it automatically requires quantization and relativity in that bracket. And this it comes from compressing the 8 global units of mass, time, charge, and space into a combined local structure, which we represent in that bracket. And the E, P, and M are just scalar factors, as I mentioned before. The real meaning is in the algebraic operators. Each algebraic operator is separate. That gives us the physical meaning. And by compressing those 4 parameters into this local picture, we create new composite parameters. That's how we get energy and momentum and rest mass, quantized versions of them. A very significant but not understood thing is that I, E, and P do not form a pure 4 vector. You cannot do the connection between space and time without having those red quaternions, equivalent to the gamma factors. So IE plus P is not a real physical object. IKE plus IP might be a real physical object, but not IKE plus IE plus P. And the connection between space and time is simply part of a bigger connection between the 4 parameters. It's like a double 4 vector, and the single 4 vector is only a classical approximation. It's not the full thing. So the 3 quaternion units have multiple but connected meanings. We've begun to see what some of them are, but here's some others. We've got P, T, and C transformations: parity, time reversal, and charge conjugation. And we can do those by using pre and post multiplications I, K, minus I, minus J, and J. Very easily you can show CP, T equals identity, and CP equals T and all that. So if we look at the 4 terms in the nilpotent force spinner, we have the lead term, and then we have, which is the real particle state, and then we effectively the transformed versions of that state, the P, T, and C transformed versions in that order, the states into which it could transform without changing the magnitude of its energy or momentum. And I see them as vacuum reflections of the real particle state. They arise from mathematical operations which we can define. Now, a fermion cannot form a combination state with itself, or it would disappear. We can only imagine it forming a combination state with something like one of these vacuum reflections. It's something like it's a copy of itself, but it's not exactly a copy of itself. And if this reflection exists or materializes as a real state, then the combined state can be one of the 3 classes of bosons. So there we are. That's the T reversal, gives us spin 1 boson. I've not put all the 4 solutions down. If I was to do this totally accurately, I would put plus and minus IK, etc. But I'll show you how that works out in another one. And then spin 0 boson reverses E and P. And the fermion-fermion combination just reverses P. And that's typically Bose-Einstein condensate, Berry phase, and all that. Now, spin 1 boson can be massless, as we would get a E squared plus P squared, which is okay. A spin 0 boson cannot be massless, as we get E squared minus P squared, which can never be, it would be 0, and we can't have that. That second equation is equivalent to 2 identical fermions. So we don't have Goldstone, but we do have Higgs mass. Interestingly, the fermion-fermion state can be spin 0 if the momenta are aligned, that's helium-3, or spin 1 if it is not, that's helium-4. Now, I'm working out a calculation for a bosonic state, including all 4 terms, to do it properly. So you just follow that calculation there. The terms on the right-hand side clearly total to 0 in IKE and JM, leaving only 8p squared, which is a scalar. So that's how we get a scalar for a boson. And it works whichever boson we use. It becomes a scalar. So we can define the entire structure of quantum mechanics by defining the creation operator for a single fermion as a nilpotent. We got 4 creation or annihilation operators, or 2 of each, whichever you want. But only the first term defines the real fermionic state. The others are the vacuum reflections into which it could transform. I'm going to look at that in a different way. If you look at the middle of the page, you can see K times the bracket, I times the bracket, J times the bracket. Those are idempotents. If I multiply them by themselves forever, they will just come up with the same answer multiplied by a scalar, which can be normalized away. And you can do that indefinitely. These behave as vacuum operators because I can put them behind the nilpotent and it won't change it significantly except by a scalar factor, which can be normalized away. So we can describe these as partitions of the total vacuum. These are the strong vacuum, the weak vacuum, and the electric vacuum. And there are various ways we can physically make meaningful those vacua. Weak vacuum, fermion creation, strong vacuum, gluon, plasma, electric vacuum, isospin, hypercharge, and so forth. So if I put a fermion, that first bracket, and then multiply it by K times itself, K times itself, K times itself forever, I will simply get the original fermion. But what I want to do is look at another way of doing that. If I take the first equation, I take the K, the first K and the second K are on either side of a bracket. If I multiply a bracket by K on either side, it flips over the sign. So the second bracket could be said to be minus K. And the third bracket doesn't have any K in front of it, so that's a normal bracket. But the fourth has K on either side, so that becomes minus. So fermion, antifermion. So a fermion in vacuum is equivalent to fermion, antifermion, fermion, antifermion, which is also equivalent to boson, 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 which is, I could do that with I or J, I'm not only doing it with K. So what we're saying here is that all real fermions have exactly supersymmetric boson partners with the same energy, momentum, mass. Vacuum partners. Each fermion is its own vacuum boson. So we need renormalization for the interactions, but we don't need renormalizations for the self-interaction. We can show that through perturbation theory, which I don't have time to do, but I can show it through the automatic cancellation of loops. So I've got vacuum energy for a particle of mass. I've got standard formula for that. To remove all these divergences, we need those things to add up to 0. Well, basically, it's getting 2j plus 1 to be 0. And if we take j equals plus or minus half for the Fermi loops, which is standard, and plus or minus 1 for the bosonic loops, then we have those values for it. And our removal of renormalization for this is simply arithmetic. It just adds up to 0. As I say, I can do it using perturbation calculation as well. I can't do it here, but the nilpotent formalization also removes the infrared divergence for propagators. The reason for that is that a nilpotent fermion times its complex conjugate is not equal to 0. It's equal to a scalar or something, and so the 1 over that doesn't have a pole. And the real reason is deep down is that equal representations of plus and minus e are happening at the same time, not in two separate places as in conventional theory. And again, I want to draw your attention to the matter and asymmetry in the universe. I don't believe there is any such asymmetry, because matter and antimatter are completely symmetric. It's just that they happen to inhabit dual spaces. And this is something I've been working on for a long time, the strong interaction. This is a combination state, which is clearly something to do with the vector nature of the p-term. If we put 3 brackets in combination, we get 0, so that can't be right. But it can be right if we split up the momentum into 3 components. And each bracket has a separate component, and we can imagine phases where the whole of the momentum is in px, the whole of the momentum is in py, or the whole of the momentum is in pz. And we can see that below. What happens then? Well, if you do that, then what you get is essentially scalar times the original single wave function. So you get px in the first one. That second one should say py. It says px, but it should be py. And the third one is pz. Notice the second one flips its sign. When the momentum operator is in the middle, the sign is flipped. And that is incredibly significant, because it means that if we want to maintain the whole symmetry, we have to have both plus and minus at the same level. Like so. Again, I should have had py there on the second one, and the second one down should be py, I think, and the fifth one down should be py in the solution. But you see, you've got pluses and minuses for all of them. And this is a clear indication, because you've got 2 helicity states for the structures. It's a clear indication that the composite state doesn't have a 0 mass. The mediators between the 6 components, it's easy to produce gluon type structures, which would look like that, 6 bosons of that form, and 2 combinations of the 3 bosons in which you've got the same p component. So these 6 phases, which are the 6 phases being those, clearly must be valid all at the same time if you're going to have rotation symmetry of space or of gauge invariance. And the symmetry is recognized to be that of SU3, with same as with 3 symmetric and 3 antisymmetric color combinations. So this solves several problems at once. And please, you feel free to nominate me for the Clay Institute Prize, because it's a lot of money. The mass gap problem, the proton must have a mass because it has to have both listed simultaneously. That's one of the that's part of a Clay Institute Prize, at least. The mass is also a Higgs type mass, even though it comes from the gluon exchange, because it It does work through a gluon exchange, but it doesn't mean that it isn't Higgs-type mechanism, because this business of having two helices is Higgs-type mechanism. Again, the strong interaction is non-chiral for the same reason, SU3 structure. I've explained that. You have to have a linear as well as a Coulomb potential, but we'll leave that out. And the zero dipole electric moment of the neutron. I have been looking at the spin contribution from the valence quark. Now, when the EMC experiment was done, which John was a member, but also some of my colleagues at Liverpool were members, I remember that result being reported right at the end of the 1980s, and I was really overcome with excitement at the possibility that I might be actually vindicated by it. Just one last thing. The standard model fermions are also in the algebra. Now, Cole-Fiore has recently been using octonions or something related to octonions to try to do this. But this is older work by me, which I've presented in this form, saying that standard model fermions are in the Dirac algebra. And I've looked at her algebra, and her algebra, though she didn't realize it, reduces to the Dirac. Now, 48 of the algebra units have quaternions. And I say quaternion is a signature of charge, which is the signature of a particle. The other 16 don't have quaternions, so they're not particles. That's space or space-time without particles. So how do you classify? We'll look at this diagram. Take the first line on the left-hand side. The left-hand side and the right-hand side is particles and antiparticles, plus and minus. That's easy. Look at the first line. You've got 3 with a blue vector. Those are the quarks. Then you've got one without a blue vector. That's the lepton that goes with them. So they're the quark lepton. And then you've got the antiparticles on the other side. The IJK, red, signify generations, and I think that's because of CPT symmetry, which in fact is what distinguishes generations. The P and T violation distinguish the second and third generation. And the other one is the I, the scalar, pseudo-scalar I, the ordinary complex I. The second line has it, the first line doesn't, the third line has it, third line doesn't have it, the fourth one does, the fifth line doesn't, the sixth line does, and that is the isospin up and down, or it can represent it. And I can do that in another way, that way, but I'm not going to go into that detail. Okay, that's it. Thank you.